G'day all. I thought I would show you a way of visualizing how greenhouse gases actually work and how we know that they are causing the atmosphere to warm up. This visualization was presented and created by some colleagues of mine, Professors Brian Martin and Peter Mahaffey, who work at the King's Centre for Visualization in Science in Edmonton, Canada. And it basically illustrates a number of different possible greenhouse gases and the ways in which they absorb and then re-emit infrared radiation. So what you can see is infrared photons flying around, the blue wiggly ones, and you can see a molecule. In this case, it's a water molecule. It's in the middle of the screen there, and we can change the wavelength of the photons that are going through. So if you look up at the top here, these are the wavelengths of the photons in nanometers. So this is the infrared band. The infrared band is just longer wavelength than visible light. It's heat radiation that carries heat energy. And in the atmosphere in particular, it carries energy away from the Earth into space. So we receive a lot of energy as ultraviolet and visible light from the sun that comes in, and in order to keep the energy balance constant, we have to have as much go out as comes in, and what goes out is in the form of infrared radiation. Now, infrared radiation is absorbed by these gases in the atmosphere in interesting ways, and this demonstration basically is about that. So this is water vapor. It absorbs in these bands. So these bands where you see fringes are the places where it will absorb infrared radiation. The places where there are no bands on the diagram are the places where water vapor essentially doesn't absorb. So if we move it to one of these bands, and just wait a minute, now you can see that the molecule has started waggling its legs. That's because it's received a photon of energy, and that photon of energy has given it energy, which it behaves as vibrational energy of those bonds within the atom. Now it can emit energy again as a photon that heads off in a different direction that would let it stop waggling as well. So, but you can see it's absorbing. The absorption goes in and puts energy into the molecule as this motion of its bonds, and then it can re-emit energy. The other thing it can do is collide with another molecule in the atmosphere and heat that molecule. Give it more energy, which is what the definition of heat is, the motion of the particles in something. So if I pull it away from that particular absorption band, it will settle down because it's not being stimulated and vibrated at that particular frequency that it absorbs at. So we know that basically there's a band down here around the high 2000s of nanometers of wavelength, and there's a band here between about 5,000 and 7,000 nanometers where water vapor absorbs. Now we can change the gas that we use. There are a number of possibilities here. We don't have methane on this particular one, but I'll show you the spectrum for methane a little bit later to give you a sense of where it does absorb. But carbon dioxide is the one we hear most about. So let's have a look at carbon dioxide. It's a different molecule shape. It's got a carbon in the middle, an oxygen on each side. It's a straight line. It's got double bonds, and it absorbs in these three bands. Essentially, because water was a bent molecule, a hydrogen, an oxygen in the middle, sorry, and a hydrogen on each side, really all it can kind of do is waggle its legs. That's the vibrational mode that it has available. Carbon dioxide has a few possibilities. It can vibrate so that the two oxygens are vibrating toward and away from each other, or it can bend, or it can vibrate so that the two oxygens are out of sync with each other. And we'll see those different modes of vibration that it can do. And those vibrations correspond to different bands of absorption. So you can see it absorbs a lot. It absorbs very deeply at a couple of bands. So this one, which doesn't overlap with the water vapor, is the biggest one in the middle here. So let's see what vibration that corresponds to. So the photons are coming through. Eventually one of them will hit it, like that. Okay, and that's the asymmetrical vibration mode. So you can see it's vibrating there. it's absorbing photons and it's releasing photons again. So it's scattering the infrared. And the key bit with that is that the infrared that's going up towards space, from Earth towards space, can be scattered and sent off in another direction instead, so that it stays in the atmosphere for longer, which is what tends to heat the atmosphere. There's another mechanism which I'll talk about in a moment. So let's have a look at these other two modes of vibration of the carbon dioxide. So we'll go down to this other band in the 2000s and go to the deepest bit and wait for a photon to hit. It doesn't seem to want to cooperate. So I'm not quite sure which vibration that corresponds to, and I can't get it to play along. All right, well, process of elimination. Let's go and have a look at the other one up in the 11,000s. No, actually the 17,000s. This is a logarithmic scale, so the divisions get further, well, the scale gets longer as you get further. Okay, so that's the waggling legs one. You can see that vibration is the the bending of the bonds rather than the straight line motion of the bonds. And that's the other mode where carbon dioxide absorbs a lot. So you can see that again, it's scattering the radiation. Now, the other thing that it can do is heat the atmosphere, and this visualization allows us to add the atmosphere. So we'll turn the atmosphere on. Now you can see the blue molecules are nitrogen. It's about 80% nitrogen, N2, and the red ones are oxygen, O2. And what's happening is it's cooling not by emitting a photon, but by colliding with molecules in the air. And when it collides with those, it heats them. If you look at the thermometer on the right-hand side, you'll see the thermometer actually increasing slowly, the temperature of the gases. Now, the temperature basically is that motion, that random motion of vibration. And it's hard to judge, but it's actually getting more frenzied. The molecules are moving faster as their temperature increases. So the thermometer helps us to kind of keep track of the fact that the atmosphere is heating because those infrared photons are being absorbed by the carbon dioxide in the atmosphere, and then that is heating the atmosphere and causing it to spread out. Now I'm going to switch to a different visualization to have a little bit of a talk about methane, but this is the absolute key bit. And if someone wants to claim that carbon dioxide is not causing heating, when we know that the level of carbon dioxide in the atmosphere has increased by about 1/3 since the Industrial Revolution, and we understand this mechanism, we know that when a photon of the right wavelength hits a carbon dioxide molecule, it vibrates in certain ways and causes the atmosphere to heat. They would have to explain this away to be able to claim that an increase in carbon dioxide doesn't cause an increase in heating. So this is a related visualization where basically we've got just the molecule itself with its diagram and the related spectrum from the molecule. There's one difference, which is that this axis, the x-axis, uses wave number, centimeters to the -1, rather than wavelength in nanometers. Different numbers, basically the same spectrum. So it'll give you a sense. So we did have a look at water before. So if I turn on water, you see the spectrum and you see those two sets of fringes, one down towards the lower end and one in the middle here. That's the water absorption spectrum. So if we turn that off again and we have a look at the carbon dioxide absorption spectrum, you'll see the same thing. The small set of fringes down at the bottom, big one in the middle, and a bigger one, a biggish one to the right-hand end as well. So that's the carbon dioxide absorption spectrum. So if you think about the carbon dioxide molecule, the ways that it can vibrate, and the infrared that it absorbs, that's its absorption spectrum. I'll turn carbon dioxide off for a moment and turn methane on. So that's the methane absorption spectrum, and it has different vibrational modes as well, and that's where it absorbs. It's interesting to think about the fact that the two of them absorb in different places. So they kind of spread out to fill the available spectrum. In the places where carbon dioxide isn't absorbing, methane is absorbing to some extent. Now, there are other other greenhouse gases as well. Water is one of them. Water we don't really control as humans, except that as the atmosphere warms, you have been studying the water cycle, as I have since primary school, and you know that heat is what drives water from the oceans into the atmosphere. So as the atmosphere warms, there will also be more water vapor in the atmosphere, and there'll be more absorption. And you'll notice that while the water coincides in some places, it fills in further gaps in other places. So we're starting to absorb a lot of infrared once we look at all of these factors. So if we take the water out for a moment, some of the chlorofluorocarbons, the CFCs, are also greenhouse gases and also absorb. Now, we got rid of a lot of the CFCs in about 1990 with the Montreal Protocol, when we decided to ban CFCs because we discovered they were damaging the ozone layer, which is a separate issue. But that's a good thing because they're also greenhouse gases. So if I add a couple of the CFCs in, there is some absorption up there that starts to fill in the spectrum. There's some absorption there, which is a similar sort of area. There's some absorption there. So that's a few of the CFCs added, nitrous oxide added as well, and so on. So you can see that there are a number. Ozone itself also absorbs some infrared. Now that's obviously much too much, so we could turn a bunch of those off. But the key point is that what this doesn't show us, it shows us where things absorb, but it doesn't show us how much. So for example, we know that methane actually absorbs, I believe it's about 25 times as much as carbon dioxide as a greenhouse gas. So although the spectral lines are the same size, the actual scope of the absorption due to methane is much greater than the scope of the absorption due to carbon dioxide for the same amount of the gas. So I hope this is helpful in giving you some sense of the real mechanics, the well understood mechanics behind climate change and why it's a great idea to stop increasing the atmospheric concentrations of carbon dioxide and methane to the extent we can as quickly as we can, because they are the things that are contributing to climate change. And it's very clear to understand how. Thanks very much. Bye.